geometrical point of the view, if this is a and B, if this is A, yes, this is the stop. Oh, and just for interpretation of that. So this is the definition for general. For general vector, sigma I squared. And if you apply that here for this example, it will give you absolute 1 plus I squared plus absolute 1 minus I squared plus absolute I squared. If you remember from the complex variable, so absolute any quantum, any number, complex number is just A squared plus B squared. Is the length of this vector actually. So you can get 1 plus 1 plus 1 plus 1 and plus 1, so it will be 5. And still it's positive. So I want to tell you that even when the component of the vector are complex numbers, then the norm of the vector is positive number. You never get minus. There is a very rare case in quantum mechanics when the norm is negative. I didn't work on that, so I'm not happy about that. Let's call it a crane space. There is a theory, and some people work crane space. So crane space basically are the vector space with the negative norm. Huh?
There you say that A dot B sometimes not equal to A dot E, not equal to E dot A.
Yeah.
You mean that continuous number, correct?
Yes, but yes. Sometimes the x, y is not y, x. Yes. Yeah. But not in normal life, actually. You can have x, y, and it will be different from this. Just in the quantum mechanics, this is called non-commutative algebra. Actually, commutative algebra is the normal algebra, huh? A, B is bare A. But why this is that? You can accept that, forget about the physics. You can accept that from now I say AB is different from BA, and you can make the whole theory based on that. This is what happened in quantum mechanics. But we are not talking now about quantum mechanics. You have a commutative and you have a non-commutative algebra. Commutative algebra is that. Commutative. And this is a non. When I explain you the matrix, when I will go to Ashton-Liouville theorem, so you will see something about the Hilbert space, and that I will explain you about the operators. So they are not normal objects, they are operators actually. Operator means that they are ready to do some work, They need some input to give you the output. But here you don't have something, you have just two numbers, A, B, and they are numbers. So they don't need waiting for something. They are just two numbers. They make the action together. So norm is positive. So during this course, we accepted that the norm should not be negative. Norm is non-negative. We talked about the norm space. Norm spaces. With the norm of the vector, you see, in 1 minute I removed the vector. For anything, for anything which satisfy the condition of the vector space, the norm should be positive. We suppose that this is positive. If still you have a doubt, you can keep it there. And if you feel free that to be ready for a more general class of the object, we call it generalized vectors, like this example of the matrix, you remember? I gave you three matrices and I told them they are working like the vector for you. For that, I don't need it to have that. For the norm, it will be positive difference. So we are working in the norm space. So and the one thing remain, and after that, we will end this today just. It was starting. There is a cross product also, not inner product. No, this I want to tell you. I forget that. I want you try to prove this theorem for me. We have a class of the object, I don't say, but they follow the vector rules. Huh? They working like the vectors. So I call it this, and this, just simple, okay? We have two objects. You can call it A and B, anything, okay? And the dot product of these two, like the dot product of the normal, I just want to write like that, okay? With any known any reason. Just that. I want you try to prove for me, or any method, that why the dot product of these two always is less than or equal to the length of the one of them multiplied to length of the other one. You know, what does it mean? A dot B squared is always less than, A squared and B squared. Yes? Exactly like that. This is just A dot B, I told you, because this is my definition. And this is the length of the A, and this is the length of the B. So I want you go and to prove that, but very generally. I want you to prove very generally. I mean this vector can have the complex number inside. Okay, they are not like they are exactly like the example which I erased it here. They can be also complex numbers. So this psi and the phi can be also what? Complex numbers. So I mean, for example, psi can be this vector. Okay, so something like that. It could have I also inside, so complex. So I want you to try to prove it generally, but you can prove, you find the proof in the book, but I want to go through and read it if you can understand that. So this is one of the fundamental things. And you can make it this interpretation for that. An elementary interpretation is that normally if we have a two vector, you know that in the basic math, so cosinus at the angle between them is defined, yes, as that, A dot B over AB, no? But just look at that, if you use this here, you can define the angle between two vectors with more than two components even. Maybe it continues to the 10, you see? So 10 dimension even, 15 dimension, anything with complex number. Huh? So you can define even cosinus theta here